Got the green light, Ephraim.
Roger. Hello, I'm Ephraim Ford, the New Mexico Electronics Division Head. On behalf of the two engineering divisions that work at the Very Large Array, let me welcome you to Antenna 28. Three things should be immediately apparent to you. One, first off, is how bright this is, so I'm going to put on my sunglasses. Second is just the size of this dish. The primary reflector that we're standing on right now is 25 meters in diameter, or 82 feet. And the third thing that you'll want to look at is obviously our quadruped legs that lead up to the apex of the antenna. There are many systems and things to discuss about an antenna, but today we're going to focus on what happens on the reflector surface and within the electronics that detect and deliver the signal that this telescope is catching. The reflector operates like an optical Cassegrain antenna, which means we're standing on the primary reflector, and above us is the secondary reflector, or what we refer to as the subreflector. Hanging below it, you will see two different sets of dipoles. Those are used for our low frequency or low band observing. The reflector, while not optically smooth, behaves like a mirror at the wavelengths we observe at radio frequencies. Going back up to the secondary reflector, its primary purpose is to turn and position itself to aim the secondary focus into one of these 8 feed horns that you can see here in the middle of the dish. These feed horns are arranged around the base of the dish, around the optical axis of this antenna. Each of these feed horns is covered by a membrane, by a radome. This helps protect it from the elements such as moisture, insects, debris. And on top of most of the feeds, you can see a feed heater. That's designed to heat off the dew, or in the case of this morning, the frost that can accumulate on some of the feeds. That moisture is very detrimental to high frequency observing, so these heaters are turned on as needed. Each of these feeds ranges in size depending on the wavelength that it is collecting. It ranges from the size of the L-band feed here to the smallest one, which is our Q-band feed. The L-band is large enough that 2 adults can stand on top of each other within it, and I estimate it can hold approximately 700 gallons, while the Q-band feed could fit in your hand. Each of those feeds is connected to one of our 8 cryogenic receivers. These receivers allow us to observe continuously from 1 to 50 gigahertz. After the collected signal has bounced twice off the primary and secondary reflectors and has gone down through the particular feed that is aimed at, it will pass through a small window and reach our electronics division's receiver. The first thing it will see is a portion of the electronics that has been cooled down to about 15 degrees Kelvin, or negative 250 Celsius. At that point, the signal is amplified by about 1,000 times before being delivered further down the electronics into ambient temperature electronics. This is done so that we can minimize the thermal noise contribution from our electronics and maximize the sensitivity of this antenna. At that point, the signal, which is now down in the vertex cabin, which is below us, is inside the receiver, as I said, is further amplified and is passed off to other electronics modules that also further amplify it, convert the frequency to a common frequency, split it, and deliver it to our digitizers. An observer has a choice of sampling at either 8 bits or 3 bits, depending on their observing needs and also concerns about RFI in the frequencies that they're observing at. Once it's sampled, though, we deliver it via the 12 fibers that come from every single pad at the site. There are 72 pads at the VLA, but only 27 of them are in use at any time when they have an antenna parked on them. Those 12 fibers deliver the signal back to our control building where they're recombined and delivered to the correlator. You'll hear more about the correlator in a later stop on this tour. So that's a very brief summary of what happens on the antenna. There are over 40 electronics modules. There are many pieces of mechanical hardware. There's miles of cabling and lots of software and firmware that are required to run all this. But the work doesn't stop there with the design and installation of all of our equipment on these antennas or in the control building. The operations maintenance of the VLA is critical to maintain the availability of this instrument for our users. That requires close coordination with the engineering divisions, with safety, with operations, staff scientists, other support staff, computing, and data analysts to make sure everything works as we want it to.